The power of large language models, LLMs, I mean, it's growing like crazy, isn't it?
Exponentially. It's hard to keep up sometimes.
Exactly. And they offer these huge benefits, right? Really transformative stuff.
Absolutely, across so many fields.
But there's always a catch. They're kind of a dual-edged sword,
That's a good way to put it.
especially now with more and more open weight models coming out.
Mhm.
You know, the ones where anyone can access and tinker with the core components.
Which opens up a whole new can of worms for security concerns, really complex ones.
Right. So today, we're doing a deep dive into this. There's a research paper, Deep Ignorance. Filtering pre-training data builds tamper-resistant safeguards into open-weight LMs. It's by O'Brien and colleagues.
A very timely paper.
Totally. And our mission for you today, listening in, is to unpack this idea. Can we actually stop LLMs from learning harmful stuff to begin with?
Instead of just trying to patch them up later, trying to make them forget.
Yeah, which seems tricky. So this dual-edged sword thing with open-weight models, it's fascinating. You get the good stuff. Transparency, research access, decentralization, all great.
Huge benefits for the community.
But then, bam, this risk. Once the weights are out, anyone can modify them. So diving into this paper, what really jumped out at you? What's the core problem they're wrestling with here?
Well, what's really striking is how the paper points out that the safety measures we've been using, you know, the ones applied after training.
And post-training fixes.
Yeah. They've really struggled. It turns out they can often be undone pretty easily.
Easily how? Like, what does that mean in practice?
We're talking maybe just a few dozen or perhaps a few hundred steps of what they call adversarial fine-tuning. It doesn't take much for someone to essentially break those safeguards.
Wow. Okay, so they're quite brittle then.
Extremely. Which, you know, raises this really important question. If those post-training methods are so easy to bypass, where else can we intervene? How can we build something more robust?
That sets things up perfectly.
Okay.
Okay, before we get to their proposed solution, let's make sure we're all on the same page about this tampering business.
Good idea.
The paper quotes another study, Jane et al., saying something like, fine-tuning rarely alters the underlying model capabilities. What does that actually imply for safety?
It's pretty fundamental. It means that even if you tweak the model, you fine-tune it so it looks like it's forgotten something harmful.
Right.
The core ability, those hidden capabilities, they're still lurking under the surface.
So they can be woken up again?
Exactly, revived.
Yeah.
And apparently quite efficiently with more fine-tuning. Think of it like putting a nice wrapper on the model.
Okay.
You're not changing the core machinery inside, just how it presents itself, its behavior.
Which makes genuine unlearning super hard for these open-weight models.
Incredibly difficult because the determined actor can just peel back that wrapper, essentially, and revive the harmful stuff.
Oh.
And there's that international AFSTICIS report, too, right? Bengio and others.
Yeah, so that mentioned.
They basically said, look, once these weights are public, forget about it. There's no way to implement a wholesale rollback. You can't just recall all the copies.
Pandora's box, like you said, once it's open.
It's open, which really highlights why we need proactive solutions, things done before the model is even released.
Okay, so that leads us nicely to their idea. If fine-tuning later is just a wrapper, what if we stop the bad stuff getting inside the box in the first place?
Precisely.
That's the deep ignorance approach they're talking about.
That's the core hypothesis. If a model never really internalizes unsafe knowledge during pre-training,
when it's first learning about the world from all that data.
Right. Then it should be much, much harder to coax harmful behaviors out of it later on, even if someone tries to tamper with it.
Makes sense. So how do they actually do that? Specifically for this biothreat proxy knowledge they focused on. Sounds sensitive.
It is. They focus there because it's a concrete example of potentially harmful factual knowledge, things related to, you know, dual-use biology, lab techniques, stuff measured by a benchmark called WMDP Bio.
Okay.
And their method was this really quite clever multi-stage filtering pipeline for the pre-training data.
Multi-stage, how did that work?
So stage 1 was basically a keyword block list. They actually use another LLM, Llama 3.370B, to help generate lists of suspect terms from known proxy documents.
Like pathogen or specific techniques.
Exactly, things like that. Then they scanned the massive pre-training data set. Any document hitting 2 or more of these block terms got flagged.
2 or more, okay.
And here's the kicker. This first computationally cheap stage cleared something like 91.58% of all the documents.
Oh, the vast majority just sailed through.
Sailed through, didn't need the heavier check, which is great for efficiency.
So what happened to the flagged documents, the other, what, 8-9%?
They went to stage 2. This involved a fine-tuned classifier, specifically a modern BERT model. This classifier was trained on examples labeled by experts distinguishing real biothreat proxy stuff from, say, general biology texts. It reviewed those flagged documents.
To weed out false positives from the keyword list.
Precisely. Drastically reduce the false positives. And what's really amazing, as you hinted at before, is the computational cost.
Yeah, you mentioned it was low.
Incredibly low. This whole two-stage filtering process, less than 1% of the total compute, the FLOPS, used for the actual model training.
That's tiny. Less than 1%.
It really makes you think. This isn't some pie-in-the-sky idea. It's potentially very practical, even for huge models.
Okay, so efficient filtering. What about the models they trained?
They trained several models, 6.9 billion parameters each. Similar architecture to Pythia 6.9b, if you know that one.
Gotcha.
And they tried a couple of filtering approaches. A strong filter, basically just the block list applied to all data, which removed about 8.4% of documents. And a weak filter, which used the block list mainly during pre-training, but the full two-stage filter during a later annealing phase of training. That one removed less data, about 5% of the annealing documents.
So they can compare different filtering intensities.
Exactly. See how much filtering was needed and what the effects were.
Right, so you got this clever sieve filtering the data before the model learns. But the big question, the one that always comes up, how do you know you haven't just made the model, well, dumb?
Yeah, the trade-off question, crucial.
Did they manage to make it ignorant in this one specific area without accidentally damaging its general smarts, like its reasoning or language skills?
Yeah.
Was there any performance hit elsewhere?
That's absolutely the critical test, isn't it? How do you measure this ignorance accurately? And just as importantly, ensure you haven't thrown the baby out with the bathwater.
Yeah.
So for measuring the biothreat knowledge, they used that WMDP bio benchmark we mentioned. It was developed by subject matter experts, covers areas like dual-use virology, bioweapons, reverse genetics, specific technical stuff.
Okay, sounds thorough.
But they were also aware of a common problem with these kinds of tests, especially multiple choice ones.
What's that?
It's called shortcut exploitation. Models can sometimes, well, cheat. They guess answers based on patterns in the choices, not actual knowledge.
Seriously? Like, how?
Get this, apparently just picking the longest answer option can give you something like 46% accuracy on some benchmarks without understanding a thing.
No way. That's okay, that's a problem.
It's a definite problem for reliable evaluation. So they specifically used two more robust test sets to counter this.
Were they?
One was WMDP Bio Robust MCQA multiple choice, but designed to remove those questions where models could guess just from the options. 868 questions there.
Okay, harder to game.
And the other, maybe even tougher, was WMDP Bio Verified Close. That's like fill in the blanks. It measures how well the model predicts the correct answer word without even seeing the choices. Over 1,000 questions like that.
Ah, so that really tests if it knows the answer, not just recognizes it.
Exactly. It's considered a much more genuine test of internalized knowledge.
All right, so that covers the ignorance part.
Yeah.
What about the general capabilities? Making sure it wasn't lobotomized.
Right. They used a suite of standard benchmarks for that. Things like MMLU, that's the massive multitask language understanding benchmark, but they removed the biology questions, obviously.
Makes sense.
Also PIQA for common sense reasoning, LAMBE for understanding text context, HelloSwag for natural language inference. Standard stuff.
Okay, a broad checkup.
Yeah.
So, what were the results? Did the filtering work? Did it break anything?
The results were, frankly, pretty remarkable. The filtering did substantially block the acquisition of that biothreat proxy knowledge.
It worked.
It worked, especially on those harder, closed-style fill-in-the-blank questions. That's where the filtered models really showed their ignorance, performing much worse, which is what you want here.
Okay, good. And the general skills?
This is the crucial part. They observed no degradation in the unrelated capabilities. Common sense reasoning, text comprehension, correct scores held up.
Wow. So surgical ignorance.
Pretty much.
Yeah.
It's like they taught the model to be an expert in almost everything except this one dangerous area.
Yeah.
Like teaching it all of medicine, but carefully leaving out how to build a bioweapon.
That is fascinating.
Yeah.
Okay, so you can prevent the knowledge getting in without making the model generally less capable. Huge step. But The real test, right?
Yeah.
What happens when someone tries to break it?
Tamper-resistance test, yeah.
If someone deliberately tries to force that knowledge back in or trick the model into revealing it, how did these ignorant models hold up against attacks? Was their resilience just okay, or was it genuinely impressive?
This is where the approach really proves its worth, I think, connecting it back to that brittle wrapper problem we talked about.
Right.
They threw quite a bit at these filtered models. 3 main types of tampering threats.
What were they?
First, latent space attacks. These are pretty sophisticated, trying to manipulate the model's internal thoughts, its hidden activations, to get the forbidden answers out. Second, good old adversarial fine-tuning. Basically, retraining the model specifically on texts full of the biothreat information they tried to filter out.
Trying to force it back in.
Exactly. And third, something called benign fine-tuning, just fine-tuning the model on normal, unrelated data, like Wikipedia articles,
I do that.
to see if the safety safeguards, the ignorance, would just fade away during normal model updates and adaptations. Does the protection persist?
Ah, okay. Makes sense. So the results. Drum roll.
Well, they were pretty stunning, actually. The filtered models showed what the paper calls state-of-the-art tamper resistance.
State-of-the-art, meaning?
Meaning they resisted that adversarial fine-tuning, the attempt to force the knowledge back in for way, way longer than previous methods.
Right.
We're talking up to 10,000 steps and exposure to 300 million tokens of biothreat text.
Whoa. How does that compare?
It's an improvement of over an order of magnitude, like more than 10 times better than the existing post-training baseline methods.
An order of magnitude. Okay, that's not just an incremental improvement. That's a leap.
It's a huge leap. And maybe even more surprising was the benign fine-tuning result.
What happened there? Did the safeguards fade?
Nope. The filtered models were incredibly robust to it. The ignorance stuck around. This is a big deal because other methods, like one called circuit breaking.
You'll probably get to that.
Yeah. Those tend to become ineffective quite quickly when the model is just updated normally. But this filtering approach seems to bake the safety in much more deeply. It persists.
That's incredibly significant for practical use, isn't it? The safety doesn't just evaporate when you do routine updates.
Exactly. It's just a much more durable form of safety.
Wow. Okay, order of magnitude improvement, robust to updates. This pre-training data filtering sounds like a really strong foundational defense, a solid shield.
It definitely seems like a powerful base layer.
So we've got this strong new shield, data filtering, but, safety often isn't about just one shield. The paper mentions the Swiss cheese model, right?
That's right, a classic safety engineering concept.
Each layer of defense has holes, like slices of Swiss cheese. But if you stack enough layers, hopefully the holes don't line up and the threat gets blocked.
Precisely. No single defense is perfect.
So even with this strong filtering, are there still ways around it? Are there still holes in this slice of cheese? And where do other defenses fit into the picture?
Absolutely, there are limitations. It's not a silver bullet. One key thing the paper points out immediately is that filtering like this, it can't stop the model from using harmful knowledge if that knowledge is given to it in context.
Ah, okay. So if I ask the model a dangerous question, and I also give it the dangerous information right there in the prompt, maybe through like a search tool.
Exactly. If you hand it the recipe, so to speak, through retrieval augmented generation or just in the prompt, the filtering doesn't stop it from using that information, even if it never learned it during pre-training.
So it's ignorant, but not incapable of processing information it's given right now.
Precisely. Which clearly shows you need other layers.
Okay, so what complements it? You mentioned circuit breaking earlier.
Yes, CB. That's a different approach. It works not by removing knowledge, but by trying to reroute the model's internal processing when it encounters harmful information.
Reroute it, like scrambling the signal.
Kind of. It tries to detect when the model is processing dangerous concepts and then interfere with those specific neural activations, effectively scrambling its ability to use that information coherently.
Wow.
And the research showed these two methods really complement each other. Filtering stops the internal knowledge, and CB impairs the ability to use that knowledge, even if it's provided externally in context.
Okay, that makes sense. Filtering prevents internalization. CB prevents utilization, even if it's handed the info. That sounds like a powerful 1-2 punch.
It is. It's a great example of that Swiss cheese model in action, layering different defenses.
Did they test combining them? What happened then?
They did. They combined filtering with CB and also with CB plus another technique called LAT, latent attack training, which is specifically designed to resist those sneaky latent space attacks.
Even stronger.
Yes, the combination yielded stronger safeguards overall. It particularly boosted resistance against few shot attacks, where you give the model just a couple of examples to steer it, and those latent space attacks.
So stacking the layers worked. But was it foolproof? Did anything get through this combined defense?
Well, here's the remaining challenge. Despite these layers, there was one attack type that none of the models resisted effectively.
Oh, what's that?
An ensemble attack, one that combined both adversarial fine-tuning and giving the model harmful information in context via retrieval.
So attacking on multiple fronts simultaneously.
Exactly. Hit it with fine-tuning and feed it the bad info in the prompt. That combination seemed to overwhelm the defenses they tested.
Okay. So that points to a potential weak spot, maybe an area for future work.
Definitely. It shows that even with multiple strong layers, sophisticated multi-pronged attacks might still pose a significant threat. Defense in depth is crucial, but maybe not yet impenetrable.
This has been incredibly insightful, really getting into the nitty-gritty of how these safety mechanisms work or don't work. Were there any other maybe surprising results or challenges they ran into? Things that didn't quite pan out as expected?
Yes, actually. One really fascinating kind of counterintuitive negative result came from an experiment they did with synthetic document training.
Synthetic documents, what's that?
The idea was, okay, instead of just removing harmful knowledge, what if we actively try to teach the model incorrect information about biothreats, like train it on deliberately wrong facts?
Oh, like trying to overwrite the bad knowledge with wrong knowledge? Seems logical, maybe.
You'd think so, right? But it totally backfired.
It did.
It actually failed to suppress the real knowledge. And in some cases, it even seemed to increase the model's score on the biothreat knowledge tests.
Whoa. Teaching it wrong stuff made it better at the dangerous stuff. How does that even work?
It's not entirely clear, but it suggests that maybe just exposing the model to the concepts and language of biothreats, even in a wrong context, might inadvertently reinforce the neural pathways related to that topic. It's a really subtle effect.
That's wild.
Yeah.
So, trying to inject misinformation is not a reliable way to create ignorance. Might even be harmful.
That seems to be the takeaway. It suggests that reliably implanting specific incorrect information at scale is really, really challenging, a very important lesson for data curation.
Definitely a surprising twist. Okay, what about other limitations of the main filtering approach? We mentioned the in-context issue.
Right. There are a few others they acknowledge. One is that filtering might not work for all kinds of harmful behavior.
Like what?
The hypothesis is that it's good against precise knowledge, scientific facts, technical procedures, that kind of thing.
Okay.
But it might be less effective against what they call emergent propensities, things like general toxicity or maybe overly compliant behavior, just following harmful instructions generally.
So behaviors that aren't tied to specific facts, but more to the model's general personality almost.
Sort of. For those kinds of issues, the model might actually need to understand harmful behaviors to effectively resist them, rather than just being ignorant of underlying facts. It's a different kind of safety problem.
That's a really interesting distinction. Ignorance of facts versus understanding of harmful intent.
Exactly. Also, a practical limitation. The filters probably have high false positive rates.
Meaning they throw out good stuff too.
Likely, yeah.
Yeah.
They might remove documents that are related to biology but aren't actually harmful proxy knowledge. So there's a risk of losing some useful, non-harmful information. Needs careful tuning.
Finding that balance.
And the last big one is scale. These experiments were on 6.9 billion parameter models, which are big, but not like the absolute state-of-the-art frontier models.
Right. GPT-4, Claude 3, Gemini, they're much larger.
Much larger. So these findings are super promising, but they definitely need to be scaled up and re-verified on those massive models to be sure they hold.
Okay, important caveats. But looking at the big picture, what are the broader implications here?
I think they're pretty significant. First, it clearly establishes pre-training data filtering as a genuinely powerful new tool in the toolbox for managing risks with open-weight LLMs, especially against tampering.
A new layer of
A
defense.
strong new layer. But second, it's just one component. It's not a magic solution, not a silver bullet. Real-world safety will still need comprehensive strategies, monitoring, other mitigations, responsible deployment practices.
As part of a bigger safety ecosystem.
Exactly. And third, it's actually relevant for closed-weight models too, the proprietary ones.
How so?
Because if a developer can use techniques like this to provide strong evidence that their model fundamentally lacks the internal wiring, the neural circuits for certain dangerous capabilities, that really strengthens their safety case.
It helps them prove the model is safe in specific ways before they deploy it.
Precisely. It's about building confidence and demonstrating safety more rigorously.
So let's bring this home for everyone listening. What does this all mean as we look to the future of AI? This whole deep dive into deep ignorance. It feels like a pretty fundamental shift.
I think it is.
Preventing the model from learning the bad stuff right from the start.
Yeah.
It seems like a much more foundational approach than just patching things up later, like building safety into the AI's DNA almost.
That's a great analogy, building it into the DNA. And while, yes, there are still challenges, those multi-layered attacks, really understanding the mechanisms of this ignorance at a deeper level.
How it actually works inside the neural net.
Right, that mechanistic ignorance. Despite those open questions, this work really puts pre-training data curation firmly on the map as a very promising and efficient layer of defense, especially for open-weight AI.
It makes us think more holistically about safety, doesn't it? Right from the very first bite of data that model sees.
It absolutely does, from the ground up.
So here's a final thought to leave everyone with. If we can reliably build this kind of targeted ignorance into AI from its earliest stages, what else could we prevent?
Interesting question.
Could we prevent biases? Other kinds of undesirable knowledge, or maybe harmful emergent behaviors? How far could this go?
That's the frontier, isn't it?
And how might that fundamentally change what we mean by AI safety or responsible AI in the coming years? It feels like the journey to truly safe AI is really just getting started.
And it might start much deeper right in the data itself than maybe we initially thought. A fascinating prospect.